Lesson 6-8, the first law of thermodynamics and simple processes. Thermodynamics is the study of laws of heat transfer and its relationship to work. Systems have internal energy due to the kinetic energy and potential energy of the particles in it. Heat can be gained by the system because of the conservation of energy. This changes the internal energy of the system. So if the system gains heat, heats energy, the internal energy would increase. Heat is positive when the system gains heat, so it's positive when we gain heat, and it is negative when the system loses heat. Work can also change the internal energy of the system. Work is positive when it's done by the system. Work is negative when it's done on the system. These aren't vectors, these are just positives and negatives. The internal energy of the system only depends on the state of the system. It's not how it got that way. We're not looking at, when we measure these, the work and the heat, it's not how we get it, it's just what it is. So our first law of thermodynamics is our change in internal energy, which is Q minus W. It's the heat minus the work. So the change in internal energy is heat minus work. Our internal energy is the 3/2 nKT if it's an ideal gas. So while working on an assignment, Frank does 10,000 joules of work. In the process, his internal energy decreases by 20,000 joules. Find the work, the change in the work, and the heat. Well, Frank is doing the work. So this is work done by the system. So work done by the system is positive. So our work is the positive 1,000. All right. Says the internal energy decreases. So our change in internal energy, it's a decrease. So that makes it a negative 20,000 joules. And then we have our change in our internal energy is heat minus work, so negative 20,000 joules equals our heat minus our 10,000 joules of work. So our heat would be negative 10,000 joules. So since that is negative, that means the system lost that much heat. He got cooler sitting there doing his homework. There are 4 thermal processes that we can use in thermodynamics. Each one is quasi-static, which means that it's slow enough that uniform temperature and pressure are maintained during each process. The first one is isobarrack. Iso is a prefix that means the same, and barrack stands for pressure, so it's the same pressure or constant pressure. For example, in our picture, we have a frictionless piston where the pressure is determined only by the weight of that block that's on the piston. So as we change our temperature, it's actually going to increase the volume of the gas and move that block up, move the piston up. So we can do work. We can apply a force over a distance, so we can do work. So the gas is heated, expands, and pushes the piston up, and our work is the force times the distance. Well, let's keep going. If our work is our force times the distance, and we're talking a gas here, or a fluid, Force is the pressure over area, because pressure is force over area, so if I multiply by A. So our work is PA times S. Well, the A is the area of the bottom, and the S is how much it moved up. So our area times the distance is our volume. I'm going to call that, it'd be our change in the volume. So that would be final minus initial. So our work is the pressure times the change in volume, or PV. So our work equals our pressure times our change in volume, and that is valid for all states of matter, not just gases. So often how this is worked with is if we use a graph of volume and pressure. I use a PV diagram. Call it a PV diagram. The work would then be the area under the graph. So if our volume changed from here to there, stayed a constant pressure, then the shaded area is the work. Our next is called isochoric. Iso again means the same, and the choric is actually standing for the volume, so it stays the same volume. You can see this little chamber in the picture, it's actually sealed. Since there's no change in volume, if we look at this little PV diagram, the pressure changes, but the volume doesn't. There's no area under that graph. So there's no work being done. Nothing is moving. So if the first law of thermodynamics is change in internal energy is Q minus W, but W is 0, that means if it's isochoric, the change in internal energy is just Q. So by changing our temperature, our pressure changes, volume stays the same. Isothermal, same. Thermal would be temperature, constant temperature. The temperature stays the same. Usually the temperature decreases as it expands, so thermal energy must be transferred into the gas from the environment. So our heat would be what does the work. It's not changing temperature doing the work. So, the heat's not changing our temperature, so the heat must then be doing work. Which means if we have delta U equals Q minus W, if those are the same, that means there's no change in internal energy when it's isothermal. Adiabatic means there's no heat transfer. If there's no heat transfer, the first law of thermodynamics becomes, well, the Q is 0, so the change in internal energy is just negative W. Sometimes it's hard to determine the type of process, or maybe it's a couple different processes that happen. So a graph could help. If you look at a graph that's pressure and volume, so this is a pressure volume graph, the area under is the work. So all that shaded area in the graph is the amount of work that occurs as our pressure and volume change. So that's the work, and then you'd have to measure how much heat went into the system or out of the system to find your change in internal energy. the process goes in a loop, then the work done is the area inside the loop on a PV graph. And here is the reason why. On coming down, the work is everything below it. Going back up, the work is there, but we're going backwards, so that would be a negative amount of work. So all that lower part canceled out, so the only work is in the middle, darker colored part of the graph. The isothermal is a positive W. The isochoric is no work, and then the adiabatic, the going back up, is negative work. So it cancels out some of the isothermal positive work and leaves just the amount in the middle. Since the work can be positive or negative, the processes can go in either direction. In theory, it could be completely reversed and return to the previous state. So think of a piston moving around. We can always move the piston back to where it was. However, there's always friction, so there's never a completely reversible process. There's always some heat lost. Heat is always lost. And so the idea in engineering is to minimize that loss. So I'd expect you to change the internal energy of the paper by doing work on it as you do the problems. That's all for today. Have a good day.